Absolutely. Big trouble. So guys, all of you just turned in your chapter 7 outlines, and we're going to get started in chapter 7. So grab your books, open them up to chapter 7. What? No. Grab your books. No. We're starting in chapter 7. No, guys, you're okay. We are starting in chapter 7, but you should have turned in chapter 8. So, ready? Chapter 6, just got done, electron structure. Go to chapter 7 and explain to me why I didn't have you outline it. Take a look at chapter 7. Why didn't I have you outline it? We've already done the entire chapter last year. Guys, chapter 7 is all about the periodic trends on the periodic table. We don't need to do that because you already know it. So what we are going to do is we are going to go over all of chapter 7 in the next 11 minutes. It's going to go relatively quickly. It's just basically going to be, you'd better know this and this and this, but it's stuff you should actually be remembering. Then, after that brief overview of the periodic properties of the elements, we are in fact going to jump into chapter 8. What we are going to do today, guys, is we are going to talk about the fundamentals of bonding, ionic covalent and metallic bonding. Guys, once we're done with that, we will have done all that we are going to do with metallic bonding. You may remember the sea of electron concept, large, low electronegative elements that just dump electrons into their free space, and you end up with these positively charged nuclei floating around in what we call a sea of electrons. That's all you need to know about metals. So what we are going to do then, guys, is we are going to spend the remainder of the day today talking about ionic bonding. You already have the concept that an ionic bond forms when a small, highly electronegative nonmetal steals an electron from a large, low electronegativity metal. That creates ions which attract, that make ionically bonded substances, which we call salts. But guys, that is only the beginning of the story. So we're going to do a deeper dive on that today. That will then conclude what you need to know about ionic bonding. We're not going to talk anymore about metallic bonding, and the remainder of this unit will be spent on the only thing that's left, which is covalent bonding and molecular structure. Got it? Go ahead. No, it means that actually, and thank goodness we don't have to talk about a lot of this anymore. In order to understand some of what's, because it doesn't dump all of its electrons, just the valence electrons. So the electrons that are core still exist in those orbitals, but then the electrons that are no longer associated with those nuclei can actually be thought of being associated with the entire substance. And thankfully, we don't have to talk about that. So, guys, follow along at home. Write down what you believe you need to. Ask questions where appropriate. Chapter 7, in a nutshell, periodic trends. First of all, atomic radii. Guys, we're not going to give this to you necessarily as notes because we know you guys are so enslaved to taking notes that it interferes with your learning. So, rather than give you the notes, you now understand we're talking about atomic radii, so let's talk about what you ought to know. So, as we go down a group, from top to bottom down a group, in any group, do these atoms get bigger or smaller? They get bigger. And why do they get bigger? We are adding energy levels to the atom. Now, guys, this is the tricky one. Probably shouldn't have said that. As we go left to right, do they get bigger or smaller? They get smaller, and now you can talk intelligently about why, given what we did with PES. Why do they get smaller? No. Why do they get smaller? Increased effective nuclear charge. right? And guys, you experienced that when we did PES because we did this, right? This is number of peaks, this is number of electrons, this is high energy, this is low energy. We said that that could be hydrogen, and if that's hydrogen, this is helium. This is the physical representation of these things getting smaller as you go left to right. Why is this peak higher energy in helium than this peak is in hydrogen? More protons, higher effective nuclear charge. So guys, PES is the experimental evidence of the fact that these do get smaller as we, or at least it's the experimental explanation for why they get smaller as we go left to right. But if you spend the time to look up their atomic radii on the periodic table, you do in fact find out they get smaller. Anything you want to talk about that trend? Okay, so here you go. Any of that you feel like you want to write down, I'll give you a second to do that, and then we're going to go on. You all good? You're good? Are you guys really actually going to take notes and not dictations over this? Because I know you just love to take dictations and write everything down. You're going to really do that? Oh, look at you guys. You're growing up. Okay. All right. So now, guys, electronegativity. Somebody tell me what it is. In slang, stealing power. Electronegativity is an atom's attraction for electrons from other atoms. We think of it as being stealing power. Oh no, now you guys are back in dictation mode. I'm going to stop clicking. Okay, so guys, we understand that there is a relationship between size and stealing power with electronegativity. So what is the relationship? What atoms are better stealers? Bitty ones or big ones? The bitty ones, right? The smaller the atom, the better the stealer that it is. And that's why we always teach you atomic radius first. Because if you know the trends in atomic radii, you also know the trends in electronegativity. Now, let's think about this. As we go down a group, do they get bigger or smaller? Bigger. So do they become stronger or weaker? Weaker. Now as we go left to right, do they get bigger or smaller? Smaller. So do they get stronger or weaker? Stronger. Now, you ready for a tough question? You now understand that as we go down this group, they get bigger and therefore weaker. Does that make them more or less reactive? It doesn't depend. Now let's do this. As we go down this group, do they get bigger or smaller? Bigger. This isn't tricky. They do get bigger. As we go down this, if we go down any group, they get bigger. So as we go down this group, do they get bigger or smaller? They get bigger. So do they get stronger or weaker? Weaker. So do these become more or less reactive? And now maybe you're seeing the point. Let's go back to the metals. As we go down, they get bigger and weaker. Does that make them more or less reactive? More reactive. Why does that make them more reactive? Well, guys, when metals react, what do they tend to do? Give electrons away, and if you're big and fat and weak, you're better at giving away electrons. So with metals, as you go down, they become more reactive because metals react by giving electrons away. Why would the nonmetals be the opposite? They react by taking electrons in, and so consequently, as you go down the nonmetals, they become bigger and weaker and therefore less reactive. That might be worth writing down, right? So guys, the thought here being the trend in reactivity does matter on what group you're talking about. The trends between atomic radius and electronegativity are not contextual. When you go down, they get bigger and weaker. But because metals react differently than nonmetals, the reactivities do in fact change. And again, guys, the idea is that the bigger the metal, the more reactive it is. The smaller the nonmetal, the more reactive. Yeah? But even what you said isn't necessarily the case, and we're going to use reactiveness because it's a nice word. So as you go down the metals, when their electronegativities go down, their reactiveness goes up. With the non-metals, as their electronegativities go down, their reactiveness goes down, right? And it becomes a question of how do they react? Metals give away electrons, so the less electronegative it is, the easier it is for them to give them away. Realize that in that context, though, we don't really call it electronegativity anymore, because electronegativity is stealing. When you're giving away an electron, what do we call that? Ionization energy. But remember, they're different sides of the same coin. So as you go down a group in the metals, they become weaker and they give away electrons better, more reactive. In the non-metals, as you go down, they become weaker and they don't take in electrons as well, and so they become less reactive. Is that okay? Okay. So guys, again, you're writing down the important bits, so I would pray that you don't try to write this down because I think you already understand it. You okay? Okay, so guys, if you are still not clear on this idea of electronegativity, allow me, largely because of the sense of pride that I have in my own creation. Do you remember the electronegativity animation of science? Oh yeah, all right. So guys, it goes like this. We understand that as we go down a group, do they get bigger or smaller? Bigger, always? Whether it's a metal or a non-metal? Always, yeah. So here's an electron, here's hydrogen, here is potassium. Potassium? Potassium. Okay. So we are going to talk about electronegativity. And when we talk about electronegativity, we're talking about stealing power. So guys, looking at an atom, if this is an electron that we are trying to steal, what part of the atom is actually doing the attracting and therefore the stealing? The nucleus, right? The nucleus being positive is attracting the electron that is trying to be stolen. So, in a hydrogen atom, you have a relatively weak nucleus, ready, that reaches out to the electron and tries to pull it back in. Now, we call that reaching out effective nuclear charge. But that is not the only force that is at play. What is the force that is preventing this hydrogen from pulling in the electron? The shielding of this electron, of the one electron around the nucleus of hydrogen. So we've got this tension between the pull of the nucleus and the push of the electrons that are already circling the nucleus. So we go down here and we look at something like potassium. And what do you know about the strength of the potassium nucleus? It's a whole lot more. So when potassium reaches out, it reaches out with a greater strength, trying to pull this electron into its orbits. But we also now have 19 electrons, and oh my goodness, that is a pant load of shielding. Now, which one wins? A simple nucleus with less nuclear charge that experiences less shielding, or a stronger nucleus that experiences increased shielding? Which one wins? The itty-bitty guy. And so we have this general principle that says simple, smaller nuclei, smaller atoms tend to be more they are more electronegative because they experience less shielding and therefore a stronger effective nuclear charge, allowing them to pull in electrons more effectively. Good? It's not the most electronegative, though. The most electronegative is fluorine. Because if you think about it, hydrogen really doesn't have any shielding, right? I mean, well, it does. It's got one electron. But the very limited shielding that you get from the electrons in the second energy level is actually low enough that fluorine, in fact, is the most electronegative element on the periodic. I think it's like 3.9 or something like that. So it is the maximum for electronegativity. All right, you guys good on electronegativity? All right, so now, guys, we need to talk about ionization energy. What is ionization energy in layman's terms? It's not stealing power, it is keeping power. It is the ability of an atom to hang on to the electrons that it's already got. We gave that another name when we did PES. What did we call it? Electron binding energy. However you choose, but guys, don't use electron binding energy outside of the context of PES. We're going to call it ionization energy, which makes sense because it's the amount of energy needed to remove an electron, stripping that electron and creating an ion. So guys, what is the trend on the periodic table as it relates to ionization energy? Well, let's just say it generically. What is the relationship between ionization energy and size? The bigger the atom, the lower the ionization energy. Guys, the same thing that makes atoms good stealers, electronegativity, also makes them good hanger-on-or-toers, keepers, ionization energy. So guys, the trend is exactly the same. So as we go down a group, they get bigger, therefore their ionization energies go down. As we go left to right, they get smaller and their ionization energies go up. So guys, it really is the same side, well, different sides of the same coin, ionization energy and electronegativity. So we got this. There you go. So guys, that was chapter 7. Now do you understand why I didn't have you outline it? All right. Well, actually, I should have had you do it, and all you would have done is just filled up the no column. We should have maybe added a 4th column that says forgot, but okay. So y'all good? Chapter 7, ready to go? Okay. So guys, chapter 8. Again, here's what's going to happen. We are going to do a brief 30,000-foot view of bonding. In a moment, you're going to need your books. So we may as well go where we need to go. And guys, the place where we need to go is page 293. Yeah. You can just have mine. You're fine. Yep. Okay. So guys, we're going to really wiki quick go through ionic, covalent, metallic. And then we're done with metallic, as I said. We're going to do covalent for the rest of the year, well, the rest of the unit. And then, guys, ionic bonding is today. So here we go. First of all, guys, what is a chemical bond? You tell me. It's actually harder than it looks. What's a chemical bond? And you know what they do, but what is a chemical bond? Maybe, but what if they're stolen? Say that again. Well, you can't use the term in the definition. What do you got? So fundamentally, guys, what do bonds do? I mean, don't talk to me as a chemist. Talk to me as somebody that understands chemistry. What does it do? Sticks atoms together, right? Okay, so what kind of force is it? Remember when we talked about forces, gravitational, all that other happiness. What kind of force is it? Is it gravitational? It's not a gravitational force. So what kind of force does it have to be? Is it a magnetic force? No, it's not North Pole, South Pole. What kind of force is it? What's making them stick together? Charges. And what term did you learn that describes charge-based attraction? Coulombic. Aha! Okay, so, guys, what we have is we have a force of attraction that exists between atoms, and it exists because of the Coulombic nature of the attractions between positives and negatives. So let's wrap it up like this. It is a force of attraction between atoms which occurs whenever two atoms or ions are strongly attracted coulombically to one another. Notice that I included the word strongly. Where? No, where? Occurs whenever two atoms. Oh! Got it. Got it. So guys, as you were trying to create your own definition for a bond, I started hearing you start to think about sharing and stealing, and that's wonderful because you were coming back to the things that you already know about bonding, because there's actually a term for that. It's what's called scaffolding. You were activating schema. Schema are actually the bits of information that you already know about a topic, and it's been proven that when we learn, what we do is we take new information and attach it to existing information, which we call schema building. Now, that's why it's actually easier to learn something about something that you already know than it is to learn about something you're not familiar with, simply because you've got nothing to hang the new information off of. So with that said, let's activate some schema. So guys, we now understand that the attraction, the bonding is an attractive force. And I think you also understand now that it exists between dissimilar charges, right? Positives and negatives attract, and we call that a Coulombic attraction. And somewhere in your brain, you know that it happens ionically, covalently, and metallically, right? Are we all good there? All of us have just activated those schema. So guys, let's talk about ionic bonding first. What are the particles, the players in an ionic bond that attract each other coulombically? A cation and an anion. Can we dig a little deeper? Which one's the cation going to be? The positive one. What kinds of atoms tend to be positive? The metals, and then the non-metal is the anion. The positive and negative attract ionic bond. Good? Okay, now, what about a metallic bond? Who are the players? What's the positive guy? The nuclei. What's the negative guy? The sea of electrons. Now, guys, check this one out because this one's hard. What about a covalent bond? Sharing what? Now we're in trouble. And the funny part is, guys, you've never questioned this. I got up in front of you last year and I said, guys, there's three kinds of bonds. There's ionic, covalent, metallic. We went through them, and I just told you, how does covalent bonds form? Covalent bonds form through the sharing of electrons, and you all went, all right, I can write that down. And you all wrote that down, and you walked away from that, and you never questioned it. And it makes zero sense. Because, guys, I told you, and you just you drank the Kool-Aid, that two electrons, do you guys know the reference on drank the Kool-Aid? Okay, so two electrons pairing up forms a covalent bond, and that's true. But heaven knows that does not create a Coulombic attraction. What's the charge of this electron? How about this one? Do they attract? They repel. So the very foundation of covalent bonding, the pairing of electrons, is fundamentally a repulsive and not an attractive force, and none of you questioned it. We're going to deal with that on Tuesday. But guys, you've got to understand, and the reason that I bring this up, guys, is because fundamentally you're going to find out that what you understand about ionic, covalent, and metallic bonding is only scratching the surface. And the easiest one for me to explain to you, the tension that's easiest for me to create first, is the tension with this concept of paired electrons. Paired electrons do not create attraction. They create repulsion. So how does that lead to covalent bonds? We'll deal with that on Tuesday. But guys, let's review this at least superficially for now so you have something to sort of hang this on. So guys, when we talk about bond types, we understand that there are ionic bonds. We're going to tell these like stories. So guys, tell me the story of the formation of an ionic bond. What happens? Once upon a time, did I ever tell? So I had this student in AP chemistry several years ago, And this was during a period, actually, well, it was even in general chemistry that they did more of this. There used to be this time where my students had to write up all of their lab reports from scratch. They had to write up all of their procedures. And so this one particular student used to write all of their lab procedures in Book of Mormon-ese. And so, step one, verily, verily, I spake unto my lab partner saying, anyway, so never mind. So, it was lovely. So, that's right. That's right. I digress. That's right. Yeah, because really it's all probability anyway, and Hebrews 11:1 all of a sudden makes sense. So, all right. So, guys, let's do this. Ionic bonding is a story. Who are the characters in the story? If a metal and a non-metal. Because, guys, if we've got two non-metals, we're telling a different story, aren't we? What story? Covalent bonding. And if we've got two metals, what's the story we're telling? Metallic bonding. So if we're going to tell the ionic bonding story, we need a metal and a non-metal. And those two things come together. And when they come together, how does this play out? What happens in ionic bonding? Which steals from whom? The non-metal steals from the metal, making the metal positive and the non-metal negative, and the positives and negatives attract, and we end up with a salt. So, just a moment. In review then, guys, an ionic bond then is this electrostatic or coulombic force that exists between opposite charges. And this happens when a non-metal and a non-metal come together, electrons are stolen, and there is attraction, which then leads to an ionic lattice. So guys, any of that you want to include in your preliminary understanding of this, feel free to jot it down. Go ahead. No, but realize that ammonium is one example of a very large category of ions that we call the polyatomics: nitrate, sulfate, bicarbonate, all the ones you memorized, right? So the idea is that when we teach this so this is not wrong. This is just too narrow. So an ionic bond is in fact an electrostatic force between ions. When we teach it fundamentally, we just talk about metals and nonmetals. But ammonium and nitrate and all the rest of the polyatomics, in fact, do form ions. But instead of atoms gaining and losing electrons, we have molecules gaining and losing electrons. So ammonium, and you understand that ammonium NH4 has a positive charge. What's going on there is that NH4 molecule is actually losing an electron in exactly the same way that metals lose electrons. And when this entire molecule loses an electron, it takes on a positive charge just like the metals do, and then it functions as an ion even though it's a molecule. Is that okay?
I sort of understood like how the chemistry works out is that it's attracted to an acid and like so. Yeah.
That's a whole other conversation, though. Just understand but it's guys, it's good we bring in the polyatomics, right? And in the polyatomics, it's just a molecule gaining or losing electrons, just like an atom can gain or lose electrons. Okay, so guys, you okay on ionic bonding? This is sort of where you are right now. We're going to go a lot deeper in about 5 minutes. Okay, so now let's do covalent bonding. This is what you already know. You know that a covalent bond results from a sharing of electrons, which hopefully now has created a crisis for you because something that you took as just being the gospel truth is actually more complicated than you originally thought, because pairing of electrons does not create attraction. It actually on the surface appears to create repulsion. Of course, we know it does create attraction because these are bonds. We just don't understand why yet. So guys, this happens when we have nonmetals come together. And the way that these form is first of all through a process called hybridization. We have not yet talked about this. It will be a part of what we're doing today, or not today, but this unit. Hybridization is then followed by the sharing process, which then leads to the formation of covalent bonds. Okay, you guys okay there? And again, hybridization is something we're going to talk about in this unit for the first time. It's actually pretty cool. You good? And then guys, finally metallic. You ready? Metallic bonding involves the delocalized bonds that exist between metal atoms which have low electronegativities and very few valence electrons. You understand that what these things do is they end up forming bonds with all of their neighbors because the nuclei are diffusely attracted to this cloud of electrons that we associate with the entire substance. And these electrons are free to move throughout the structure, throughout the structure of the metal, which explains everything we need to know about metals. That's why they conduct, that's why they're shiny, that's why they're ductile, that's why they're malleable, because these electrons are just spread diffusely throughout the substance, and we look at pictures that look like this. You're now done with metallic bonding. Are you ready? Not yet. How about now? You guys all okay? You're good? All right, so guys, for the rest of the day today, what we are going to do is we are going to do a deeper dive on ionic bonding. You have a sense that ionic bonding involves a transfer of electrons that creates ions, that creates attraction. But guys, in a way similar to the tension that I created with you with covalent bonding, I want to create a tension with you relative to ionic bonding. It's not a similar tension, but it is a tension that you need to be able to resolve. So I would encourage you to please not take notes. For some of you, that may require putting down your pencil and literally sitting on your hands. If you need to do that, please do. Because guys, this is an idea that you're going to understand unless you're so focused on your paper that you're not a part of the conversation. So become a part of the conversation. So ionic bonding, guys, we're going to take us back to a place where I think most of us feel comfortable. We understand that the most familiar ionically bonded substance to us is our good friend table salt. It is so familiar that we in fact call this salt, when in fact salt is an example, table salt is an example of that larger class of ionically bonded compounds that are really appropriately called salts. So, how does table salt form? Well guys, you understand that sodium's the metal, so what is it going to do? Lose an electron. Chlorine is the nonmetal. What is it going to do? It's going to take in the electron. So guys, as we begin to play this game, ready, watch close, we've got sodium with 1 valence electron. We've got chlorine with 7 valence electrons. I left out the core electrons for clarity. When these come together, the 1 electron from sodium is effectively transferred to the chlorine. Now, because you guys just got through chapter 6, you can have some intelligent thoughts about what you just saw. You ready? So let's do this again. That 1 electron in sodium is in the 3s sublevel. And in order for us to take that one electron in the 3s sublevel of sodium and get it to go to the chlorine, what do we have to do to it first relative to the sodium? Strip it away from the sodium. We've got to ionize it. And so, guys, you should be having this amazingly rich experience where you think about the idea of how much energy do we have to add to that 3s electron to get it to go to energy level infinity. How much energy does that take? Ionization energy. So guys, this isn't just something that happens in discharge tubes when you're thinking about Bohr atoms. This is literally the amount of energy that it takes to take this electron from energy level 3 and kick it up to energy level infinity and boot that bugger out of the sodium atom. So the amount of energy that it takes to make that electron go from here to away is ionization energy. Yeah.
So does that mean that the chlorine, I thought it was just because of, you said it was just because of charges.
But the charges don't even exist yet. We're talking about how the charges form. Yeah. Let me keep going. So sodium has to lose its electron, right? And in order to get that electron out of sodium, we have to add energy. How much energy do we have to add? Ionization energy. Now, as such, is that process of losing this electron endo or exothermic? Let me ask it again. Is the process of electron removal endo or exothermic? Endothermic. If we want this electron to go to energy level infinity, we've got to add energy to it to get it to go up there so that it can go away. You good? Okay, now this electron doesn't just float around then in space, right? And actually, I've sort of clearly animated it that way, that as soon as it's free of the sodium, it goes into the chlorine. But you can actually think of that as being two separate processes. So guys, when we add the energy to the sodium, the electron goes away. Then you can think of it as being a free-floating electron that then falls into the chlorine. And it falls from, now we're relative to the chlorine, it falls from energy level infinity all the way down to the 3p in the chlorine atom, completing the 3p sublevel. So now let's talk about the chlorine. When that electron falls into the chlorine, is that going to give off energy or take in energy? Give off energy. In what form, by the way? Light. Okay. But, so as that electron falls into chlorine, it re-radiates that energy in the form of light and a little bit of heat. But is that an endo or an exothermic process? That is an exothermic process. The electron, and you already know that, when electrons fall, they release energy. Guys, this is all about what you learned in chapter 6. So this electron goes away, that is endothermic. The electron falls into chlorine, that is exothermic. You get the idea? Now, here's the question. Hess's law. Remember Hess's law? If you can add up the energies of the steps, you can figure out the energy of the overall process. You're good? Now let's talk about the entire process. So, sodium losing electron, chlorine gaining electron, those are the two things that have to happen in order for table salt to form. What will determine if the overall process is endo or exothermic? The difference between the two. So you ready? If removing the electron from sodium is greater, if the energy needed to remove the electron from sodium is greater than the energy released when chlorine gains it. Let me say that again. If this amount of energy going in is greater than this amount of energy coming out, will the overall process be endo or exothermic? Endothermic. And conversely, if the amount of energy released by this is greater than the amount of energy absorbed by this, will it be endo or exothermic? Exothermic. Now, with that in mind, let me show you the process. right there. Here we go.
Sodium metal is heated until it melts and just begins to burn.
Okay, so what we have here is we have a piece of sodium. And what they're doing is they're actually adding some heat to it. It's actually kind of cool. It's in a clear it's a Lexan, not Lexan, but what's it called? Pyrex. It's in a Pyrex crucible with a handle. Kind of fun. And they're heating this thing up. And then what do you suppose is over there in that big old graduated cylinder? Chlorine gas. So they are going to put the sodium metal, now that it's heated and melted, into the chlorine gas. You're going to see the sodium react with the chlorine. Oh, poop. Or you're not.
Sodium metal is heated until it melts and just begins to burn. Then it is immersed into the yellow-green chlorine gas. The sodium begins to burn in chlorine with an intense yellow flame.
Okay, so now you see the reaction between sodium and chlorine. By the way, see the smoke? What's the smoke? Table salt. That smoke is table salt. So as the sodium reacts with the chlorine, you're seeing the formation of table salt.
It produces a white smoke of sodium chloride.
Now here's the question. Is it endo or exothermic, this process? The formation of table salt, is it overall endo or exothermic? It is overall. How do you know? Because it looks like it's on fire, right? It's given off bamboozles of energy. And that energy being given off tells us that it's exothermic. Are you all satisfied with that this is exothermic? Is that okay? You're all okay? None of you are going to argue that later, right? You're all okay with the idea that this is exothermic. But yes, you are going to regret it. Okay, so here we go. You ready? Let's explain it. Tying back to what we know, and again, we're all on the same page, it's exothermic. Guys, if that's true, which one of these has got to be greater in energy? The removal of electron from sodium or the addition of electron to chlorine? And let's talk about why. This is endothermic, right? If this was, in fact, the one that was greater in magnitude, the reaction would be overall endothermic. But because we see that the overall reaction is exothermic, it must be the addition of the electron to the chlorine that is greater in magnitude, right? Y'all get the logic? Because it's completely wrong. Here's why. Guys, we all understand that this reaction is in fact exothermic, and you don't get to argue that anymore because you all said you agreed. Now, the problem is this. We understand that losing electrons is an endothermic process. Again, to make sure you're clear, how much energy goes in order to lose the electron? Ionization energy. Now, the gaining of this electron is an exothermic process. So if we're tying this together, because the reaction is exothermic, we would expect the gaining of an electron to be larger in magnitude. Turns out that that's not the case. That losing the electron, let me say it differently, removing the electron, better word, removing from the electron from sodium, in this case, tends to be more endothermic than gaining the electron is exothermic. So now we've got a problem. Second. Now we have a problem. There is more energy going into getting the electron off of sodium than there is removing or adding the electron to the chlorine. And yet, this process is clearly exothermic. So what's going on? Go ahead, Caleb. Yeah, that's typically the case. Yeah, so yes. Go ahead.
So, I'm just going to say that let me split on it here. I'm going to say that it comes from the entropy of the two elements because, like, they're both super reactive.
Good for you.
Which means they got so much potential energy.
Mm-hmm.
From the salt, they're like, oh my goodness, I'm stable now.
Good for you. And it is a question of entropy, but you're not quite there. Other thoughts? What could possibly explain this experience that is seemingly contradictory? Yeah. Well, you saw the fire. It's good stinking night exothermic. Very exothermic. Maybe we could agree on this. If nothing else, we understand, and this is a good scientific principle. Some of you are actually going to be doing science for your life, so good scientific principle. We have a hypothesis. The hypothesis is that the removal of the electron is endothermic, the gaining of the electron is exothermic, and consequently, if we see a reaction that's exothermic, then the gaining of the electron should predominate because that's what we're seeing in the actual experiment itself. So guys, when you run into anomalous data that doesn't support your hypothesis, what do you do first? Do your experiment again. I'm not going to show you the video again. It's the real deal. So when that happens, what do you then have to start to do? Rethink your hypothesis. And guys, many times what happens is this. It's not that your hypothesis is wrong, it's just incomplete. And guys, that's what's going on here. So follow the thought. If the formation of table salt was simply the creation of ions, then this reaction would be endothermic. It takes more energy to pull the electron off the sodium than it does to put the electron in the chlorine. So if that's all it took to make salt, if all it took to make salt was to make ions, it would be endothermic. The problem is with our understanding of the formation of salt. It doesn't stop here. So guys, let me show you the whole picture. Are you ready? My left hand is sodium. My right hand, it's on your left. This is sodium and this is chlorine. Sodium takes in energy, and what happens? The electron goes away. And then that electron comes over here and it falls into the chlorine, and what happens? Energy is given off. Guys, here's the thing you've got to understand. At that point, we have not created salt. What have we created? Ions. But now we're ready to create salt. And when the salt is created, these ions now attract each other. But it doesn't stop there, because one sodium does not just attract one chloride. In fact, what happens is this. See that little sodium inside there? One sodium actually orients itself with 6 chlorides. And then if this thing were large enough, you would find out that one chloride orients itself with 6 sodium ions. And you have this multiplying of bonding interactions all going on, and all of a sudden, as Spencer pointed out, you've got all these ions that were originally randomly distributed throughout the space, organizing themselves as a crystal. And guys, we understand from chapter 19 that organization, which we call what? Entropy, is a very real thing with energy associated with it. And so when these unorganized ions come together to form this very orderly structure, which we call a salt crystal lattice, pant loads of energy is given off. How much energy is given off? Enough energy to create the flame that you saw in the video. Do you get the idea? So guys, the bottom line is this. Is energy taken in when sodium becomes sodium ion? Absolutely. Is energy given off when chlorine becomes, given off when chlorine becomes chloride ion? Absolutely. But guys, the taking in of energy is greater than the giving off of energy. The reason the entire process is exothermic is because it doesn't stop there. The sodiums and the chlorides bond together, forming this amazingly stable low entropy lattice. And it's that release of energy that causes the overall process to be exothermic. Do you understand? Then let me pause and let me give you a moment to write that stuff down in your notes. You need to summarize that. Guys, the question that you're asking is, why, and you don't need to write down the question, it should be implicit in your answer. Why is the formation of salt exothermic if the formation of ions is endothermic? That's the question that you're addressing. Guys, make this make sense in your own head and get it on paper. Why is the formation of salt exothermic if the creation of the ions that forms the salt endothermic? Anyone feeling brave? No? Come on. I want to know what you wrote. Read it. Anyone brave? Oh, Waldo.
Ionic bonds are exothermic because delta S is extremely negative for the reaction, even ion formations.
I like it. Okay. But here, let me suggest a thought. When I think of ionic bonds, at least in my brain, I'm just thinking of one sodium bonding to one chlorine. Yes. It's all about the multiplication of orientation that happens in the formation of that larger crystal lattice. Yep. I think that's an important thing to include is that it's the lattice, it's that macro scale that is so not entropic. Anything else you want to add? You guys good? Okay, so guys, now we need to think about this predictively. Or do you need another minute? Can we do predictive, or tell me when you're ready. I'll be up here if you need me. That would be a nice time to have a snack. I don't have any snacks. You guys done? Okay. So guys, this then is what we're talking about, right? We are talking now about the formation of this wonderfully organized thing that we call a crystal lattice that brings so much organization to all of this that the amount of energy that's released is so unlike the amount of energy involved in ion formation. Now, guys, let me share it with you this way. And Taylor, if you're finding this is still a little nutty, try this on for size. This may help. Guys, this is a graphical representation of everything that we just talked about. Let me let you sort of drink it in for a minute, and then we'll talk about it. By the way, guys, just so you know, it starts here. That's the starting line. Do you see it? Let's talk about it. This is fascinating. So guys, what is this? This is solid sodium and chlorine gas. This is what you saw at the beginning of the video. The sodium in the crucible, the gas in the beaker or the graduated cylinder thingy. Now, what we've done is we've taken this entire process and broke it into steps. What does it mean if we're moving up? Is energy going in or out? Going in, that would be endothermic. So guys, really the first endothermic step is to take this solid sodium and turn it into a gas. Technically, that is necessary for this to happen. They actually liquefied it with the Bunsen burner. Some of it, in fact, did vaporize. So this is technically the boiling and then vaporization of the sodium. So then we go from there to here. What have we done in step number 2? Split the diatomic chlorine into chlorine atoms. So this probably mentally is where we are starting to think about this. And if we could get our hands on sodium gas and chlorine gas, not diatomic chlorine, that would be our starting point. At least this is where we started in the stupid little animation that I did. Now, endothermic. What happened between points 3 and 4? Ionization of which one? The sodium. That is the amount of energy that it took to rip the electron off of sodium, which we call ionization energy. And sure enough, it was endothermic. So now we've got this electron chilling in space. And then what happens next? The electron falls into the chlorine. That, as we identified, is an exothermic process forming chloride ion. Now, if that was where the process ended, then we can see that the net change between the elements and the ions is actually endothermic. That was our previous tension. But we now understand that it doesn't stop here. It goes, whoa, all the way down to there. And what is all of this energy? It's the amount of energy that is lost in the form of order, if you will, as the lattice forms. And it's all of this energy right here that causes the overall process to be exothermic. Do you see it now? Taylor, is that helpful? You guys okay? Yeah. No. So let me take a swing at it this way. We understand. Let's talk about it. So guys, when this happens is let me say this right. When this happens, is disorder going up or down? Disorder is going down. Right? Good night. Making this. So what do we know is got to be happening? Well, as this happens, what is it releasing? Heat. You saw it, right? The video heat. And guys, as it releases heat, what does that heat do to the surroundings? Excites it. And as the surroundings excite, what happens to the entropy of the surroundings? It goes up. And it goes up more than the entropy of the ions to the lattice goes down. And we know that has to be the case because it's spontaneous. So in fact, we're not violating this idea that entropy has to be going up. It's just that it's the entropy of the surroundings that are going up and not the entropy of the system, which is our salt. Entropy is Entropy is, you could think of it that way, entropy is being transferred from the decreasing disorder of the salt to the increasing disorder of the surroundings through the avenue of heat. You guys okay? Okay, so in addition to being able to understand all of that, guys, what you've got to be able to do is understand this table. It's the thing I had you open to in your book. So guys, take a look at this table. The colors are different, but the information is the same. What page is this on? 7 what? Oh, 290, okay. So, guys, what you've got in front of you, as the heading would indicate, is you've got a table of lattice energies. The first thing that I'd like you to do is struggle with the fact that these numbers don't make sense. Guys, look at all the numbers. You've got salts, right? Down the left-hand column, you've got salts. Notice the columns repeat themselves. So the first and third columns are the salts, and the second and fourth columns are their lattice energies. But guys, why are those numbers troubling in general? They're big, but we know they're big. We saw the fire. I don't like them for a whole nother reason. What's the problem? What about it? Hi. Thank you. Yeah. Keep going. Right? Yeah. Yeah. So, guys, whenever we form a lattice, it will always be exothermic, right? And what's the value for delta H for an exothermic process? Negative. And what are all the values in that table? Now we have a problem, right? They're all backwards. Why are they backwards? Well, guys, let me explain to you why they're backwards. Turn over to page 292. Not turn over, just glance over. And you see the word lattice energy? And then read the definition that's in italics. Do you get it now? I don't have my book, so Jason, you get to read it out loud because you have my book.
Is the energy required to completely separate 1 mole of solid ionic compound into its gaseous ions?
Do you get it? So guys, the idea is this. When you just learned about lattice energy, we talked... Parker?
Sorry, really dumb.
No, I was waiting for you to giggle.
I was giggling.
Not loud enough. Okay, so guys, this is what we talked about, right? We said that lattice energy is the amount of energy that's released when the lattice forms. But given what you and then Jason read out loud, how are they defining lattice energy? How much energy it takes to break the lattice apart. But isn't that the same? The amount of energy that's released when the lattice is formed is equal to the amount of energy that's taken in when the lattice breaks apart. So the bottom line is that the numbers hold true. The magnitudes hold true. We're just looking at them through the lens of lattice destruction rather than lattice creation. Okay? Now with that said, they will ask you questions on the test about which of these salts would have the highest lattice energy. Which one of these salts would be the most stable, therefore having the highest lattice energy? Here's the problem. They're not going to give you tables. They will not give you data. They expect you to understand comparatively. They would never ask you, what is the lattice energy of lithium chloride? But they would ask you, which of these two salts has a higher lattice energy, sodium chloride or lithium chloride? So what we need to find, guys, is the trends. There are two predictive indicators of lattice energy, and they aren't the same. One is more predictive than the other. You need to find both. Take a second, look at the data, find the trends. Not yet. What characteristic properties of a salt, well, or at least the atoms that make up the salt, would seem to predict the magnitude of the lattice energy for that salt? Now guys, as you're thinking about this, because we understand that the end game here is that we're getting ready for May, right? May is coming. What I want you to do is I want you to formulate a response to that question that would satisfy the needs of an AP grader. So you want to talk about the trials that you're looking at. You want to talk about the relationships that you're drawing upon. It's not enough to just say, oh, it's this. You've got to be able to support that answer with evidence given the data. So let me give you a second to think about it. This isn't time sensitive. Can we talk? Okay. So guys, how many of you, as you were looking over, and we're just going to call this the first column of data. How many of you, as you were looking over the first column of data, figured out that it is in a very controlled and repetitious order? Do you see it? Lithium, 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 sodium, 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 potassium, 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 cesium, cesium. What are all of those let's just call them metals because they are. What are all of those metals? They're the alkali metals, and conveniently enough, they're in order from top to bottom. That's nice. Now, what did they give us over here in the right-hand column? Well, for the non-metal. They're all halogens, also in order. So, what we could identify then, guys, is that this data can actually be broken up into 4 sets. We've got lithium salts, sodium salts, potassium salts, and then the cesium salts. Then we've got controls. In the first set of data, what's our control? What's our control here? Lithium, and then sodium, and then potassium, and then cesium. So let's then narrow this down to our first set of data. Lithium is our control. What's changing? The halogen. And what is happening to the lattice energy of these salts? Going down. So, because lithium is our control, what must be causing the lattice energy to go down? Something about the halogen. So, now we can go over and we can look at these halogens. Fluorine, chlorine, and then they didn't give us bromine, they went down to iodine. So what do we know about the halogens as we go down the group? They're becoming less electronegative and bigger and weaker. And go, wow, you guys learn. Yes, less reactive. So now, guys, this is the point at which you need my guidance. Because you understand that very well, you understand. They're becoming weaker, less reactive, bigger, lower ionization, all of these things. So which one is it? And the answer is size. Guys, size is the deal. So now let's talk about size. As we go down, are the atoms getting bigger or smaller? Bigger. And what's happening to the lattice energy as we go down? They're getting weaker. The lattice is getting weaker. The question is why? And guys, think about it this way. The halogen in table salt, the chlorine, is represented by the green guy. Now, if we took out these green guys for chlorine, and if we replaced them with, say, for example, iodines, how would the iodines compare to the green chlorines? They would be bigger. And because they're bigger, the lattice is not as tightly packed together. The attractions between the positives and negatives are weaker, and therefore the lattice is weaker. You get the idea? So maybe we should write that down. One of the predictors, you figure out, don't do this word for word, but one of the predictors for lattice strength is the size of the ion. And what is the relationship? Is it direct or inverse? It's inverse. The bigger the ion, the weaker the lattice. So maybe all you need to write down is the bigger the ion, the weaker the lattice. Now, if that's true, it should play out in our other examples. So let's look. Here we have sodium, 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 sodium. And as we go down, these are also in order top to bottom, right? Small to big. Is that true? Fluorine, chlorine, bromine. Good. Okay. And are they going down? Sure enough. And that's what I wanted to talk about now. Because, guys, does this only work with the anion? Well, let's check our cations. So here's fluorine, here's fluorine, here's fluorine, and we'll stop there. So now we've got lithium, sodium, and potassium. Again, we're going down, and if this works, we should see a decrease there as well. And sure enough, we do. So it's not just relative to the anion, the trend holds true with the cations as well. You're good? Because that's only half the story. Now, guys, let's take these into consideration. We've already established the size-strength relationship, and those carry through to these as well. Magnesium is smaller than strontium, and therefore the energy is higher for magnesium. But what do you notice about these energies in the second set of data? They're huge, which means we just found another major predictor of lattice strength. Because, guys, while these were changing, they were only ranging by about a 40% difference across the entire data set. Now we're talking about doublings and triplings and septuplings of energies. So we found something bigger than the size of the ion. What could it possibly be? Although noticing that the size trends still work. But what's the bigger predictor? Charge. +2, -1, +2, -1. The cation now has a +2 charge. Way stronger attraction. What about this? +1, -2, +1, -2, +1, -2. Oh no, I'm sorry, +2, -2. And now they're even stronger. And then, guys, +3, -3. And they just keep getting stronger as the magnitudes of the charges go up. So, we now have something else to add to our notes. What is the other predictor of lattice energy? Charge. Is it direct or inverse? Direct. And is it the major or minor predictor? Major. So the major predictor of lattice strength is the charge of the ions, and it's a direct relationship. All right. So guys, with all of that said, here's your homework. Now guys, understand that contained within this homework assignment, you will see a couple questions about the sizes of ions. You ready for a groundbreaking thought? If you have a sodium atom, if it loses an electron, will it get bigger or smaller? Smaller. If you have a chlorine atom and it gains an electron, will it get bigger or smaller? Bigger. If you lose electrons, you get smaller. If you gain electrons, you get bigger. You'll see questions in homework. Guys, we will grade this on Tuesday. Just a second. We will resolve the seeming tension with covalently bonded stuff on Tuesday.